My friend Larry Wasserman. Larry is UPMC professor in the Department of Statistics and Data Science and Department of Machine Learning at Carnegie Mellon University. Oh no, right. He received his PhD in 1988 from the University of Toronto and has been at Carnegie Mellon since then. He's won many awards, including the COPS Award, the CRM SSC Award. He's a fellow of ASA, IMS, AAAS, and in 2016 he was elected to the National Academy of Sciences. He works in non-parametric inference, asymptotic theory, and applications to astrophysics. And interestingly enough, there is another Larry Wasserman, who is an astronomer at Lowell Observatory. So he got his PhD in 1973 from Cornell, not the same guy. And he's the author of 2 books, All of Statistics and All of Non-Parametric Statistics, very modestly named. I remember when the book All of Statistics was coming out, and Larry wanted to put a picture of an olive on the cover of the book. Olive. And Springer said, no, that doesn't match with our brand, so they didn't let him do it. But he snuck it in because it's in the index. And it's actually in the index of all of non-parametric statistics too. So if you go to the index of those 2 books and look under O, you will see an entry for olive. And that's because Springer wouldn't let him put it on the cover, so he snuck it in the back. So without any further ado, let's welcome Larry. He's going to talk about local minimax testing.
Do you need the mic? Use this one, okay. Well, I think I talk loud enough anyway, probably. Thank you very much, Nicole, for the very nice introduction. She gave away the secret of my index. I've been waiting for 14 years for somebody to notice that, and so finally somebody has. So thank you for inviting me. It's an honor to be here, and thank you very much for the hospitality. I've had a very fun day talking to lots of people and seeing your new digs. Very nice, bright space. And so now, I'll get on to what I'm supposed to talk about. I want to spill this on my computer. Okay, so what I want to talk about is local minimax testing. This is joint work, I want to say, with my young colleague, Sivaraman Balakrishnan at CMU. Let me first put this into a bit of context. Well, I talked to a number of people today, and whenever I get a chance to say this, I go on my religious quest, which is that there's too many assumptions in statistics, and I'm always trying to get rid of assumptions to the degree that I can. And that's, in the last few years, I've had sort of 2 main research threads. One of them is about trying to create methods that don't make a lot of assumptions, that are distribution free, which is not what I'll talk about today. And the second thread, which is what I'll talk about today, is to take current methods and to try to see how do the assumptions affect things, what happens if we try to relax them a bit. And that's what we're going to talk about. So now specifically I'm going to talk about something I never thought I'd be talking about, which is first of all hypothesis testing. And the other one is just testing multinomials, which both seem like kind of 1920s sorts of things. And it might be surprising that there's still things to learn about these things. And I have to say, when my young colleague, Siva, came to me and said, we should look at this, my first reaction was, are you crazy? We know everything about this already. And he said, no, I'm not sure you do know everything about this. And he turned out to be right. In fact, a lot of our work is motivated by some recent work in theoretical computer science. That's how this started. He said, look, there's been some really interesting work in theoretical computer science about testing multinomials. And literally my first reaction was, what have we possibly got to learn from a bunch of computer scientists about multinomials? We solved this problem 100 years ago. Luckily, he was persistent. He said, no, you really should take a look at these papers. And finally I did, and I said, there is something interesting going on here. And so what we've been doing is, I'll actually start by summarizing some of the CS theory results and then talk about our work, which builds on that. So yes, CS people are pushing the boundaries of statistics. And by the way, when I talk about theoretical CS, I don't mean ML. I'm not talking about machine learning. There's a whole entirely different community of theoretical computer scientists. Okay, so I'm going to talk about hypothesis testing. And then the first one is going to be, these are just two pictures of two high-dimensional multinomials, lots and lots of categories. And the key being something not unfamiliar, that the number of categories, D, can often be larger than the sample size, N. And that's specifically what I want to focus on, is when the number of categories is very large, possibly even infinite. And the goal is to understand, again, the role of assumptions here and the fundamental limits of what we can do. So commonly made assumptions would be, if you're in the testing literature, a uniform null, or fixed cells, which is the number of cells can't increase, or the number of cells D can increase with N, but there'll be extra assumptions typically loaded in to ensure we get limiting distributions that we're familiar with. And it turns out that that has very non-trivial consequences, and the goal here is to get rid of that last thing. And we'll do a similar thing for density. So again, we'll talk about a really simple case. We're just going to draw observations from a density, and just the simplest problem. Did it come from this density, yes or no? And we're going to be looking at the testing framework, and we're going to see that a lot of the really important work here was done by Inkster, who I think only passed away a few years ago. I can't remember if he was Lithuanian or Russian, but devoted a lot of his life to proving impenetrable theorems about minimax testing that we had to go through. But he did make some assumptions like bounded domain, basically a uniform null distribution, and very strong smoothness assumptions, and it's going to turn out those things are not so innocuous, and that's what we'll be talking about. Let me say a word about why I'm talking about testing. Well, of course, there are some cases where you want to do testing, but nonetheless, it's not something I would say I do a lot of, and in fact, I typically tell students when I'm teaching courses, don't use hypothesis testing. Usually it's confidence intervals or things like that we're interested in. Hypothesis tests are not informative enough, and so on. And here I am talking about it. But the reason really is that this is part of a broader goal, as I mentioned, which is understanding how strongly the assumptions affect the kinds of things we're familiar with. And to answer that question really clearly just turns out testing is a good starting point. You're going to see that we can express some of the concerns we have very cleanly and very clearly by working in a testing framework. So you should think of the testing framework here as just a device so we can talk about things clearly. But it's really just the first step. We're going to eventually get beyond testing, not in today's talk, but in my work I hope to. But it turns out there are even surprises in the testing framework. So this is really just a first step. And one of the main questions we're going to ask is when we start to loosen up the assumptions is say, how does the statistical difficulty of a problem vary across the parameter space? And this is where the word local comes in, because a lot of minimax theory doesn't matter where you are in the space. The difficulty of the problem is sort of constant across the whole space of functions you're working with or whatever. That's not going to be true here when we look at it from this point of view. It's going to turn out that some parts of the parameter space are very, very easy to test, and some parts are very difficult to test. And we want to look at things at a fine enough resolution that we can see those differences. So how do the assumptions precisely affect the difficulty of the problem? I'll just mention there's a couple of references here. I can send them to you if you're interested. One is in review of the Annals. The other one is more of a review paper, which is to appear in the Annals of Applied Statistics. All right, so the basic setup is going to be, again, one of the simplest problems in statistics, which is, maybe it's the simplest problem statistically speaking, which is I have a sample from a distribution. I'm going to pick a single fixed P0, not even a composite null for now. A single fixed P0, and I just want to test the data come from this P0. And the alternative is going to be, well, to study the power, of course, I have to consider things that are at least some distance away from the null. And we're going to use the total variation distance for a variety of reasons. I think it's a very natural distance to use, actually. But it is distance dependent. We have results for other distances too, but I'll focus on one distance. So just the total variation distance. Just to remind you, total variation distance between two distributions is just the maximum difference between P of A and Q of A over all of n's A. And so that's, throughout the talk, that's the only distance I'll be talking about today. So we should think of the null as, again, it came from this particular distribution. The alternative is it came from a distribution epsilon away. in total variation distance. So again, total variation, I think, is a natural metric. It's invariant to scale. It has a clear interpretation probabilistically. But as I just stated it, we know from results by Lacombe and others that the way I pose the problem right now, it may not be well defined in general. In fact, there'll be no test that has any power against that alternative, unless we look at some special cases with more structure. And again, I'll just remind you, the metric does matter, and I'm happy to talk about other metrics later on if you want, but for this talk, we'll focus on this. So we need some structure, and I'm going to consider two. The first one is kind of necessary to get to the second one, and that's what I was talking about at the beginning, which is multinomials. So we're going to look at the set of all probability functions p, just think of them as vectors of length b that sum to 1. We should think of d as being large relative to n, potentially. So there'll be d categories. And then the other one will be the density framework, where we're going to look at the set of all density functions on Rd, let's say, and we're going to put a minimal amount of smoothness. We're going to assume that it's Lipschitz smooth. But now let's just mention what some of these common assumptions that are made in the literature, in the existing literature. So in the multinomial case, as I said, the uniform null is commonly assumed, and that turns out to matter a lot. And typically d is fixed or not too large. We want to get rid of that. In the density case, again, uniform null, bounded domain, and in this case, the Lipschitz constant L is often held fixed, and we're going to try to get rid of these things. So we want to weaken all those assumptions and then see how the risk depends on the problem. So we are doing a testing framework, so I'm going to be working with tests, which are just functions, obviously, that are take values 0 and 1. I'm going to assume that we fix the level of the test at some arbitrary level, alpha. So we're only dealing with, some say, 5% tests, for example. And so capital phi n will denote all level alpha tests. And now I'm going to look at my minimax error, which is simply what's the biggest type 2 error over the alternative. So I'm just taking the largest type 2 error over all 5% tests. That's what Rn is going to represent. But, and then I'm going to, so at this point I've fixed epsilon. I said, let's look at a fixed distance epsilon. So up to here I fixed epsilon and said, what's the maximum type 2 error? Now I'm going to say, how small can I make this epsilon and still have non-trivial power? That's the thing we're actually going to compute. So we'll call that the local minimax rate, or the separation rate, or the critical radius. It's just saying, how close can I get to the null and still have non-trivial power? That's the thing we're going to compute throughout the entire talk, is this epsilon n. Notice that it depends on the null, p0. I've written it explicitly as epsilon n of p0. That's the local, in the title, local minimax testing. We can also look at the more traditional minimax quantity, which would be the global minimax rate, which is just now to look at the worst case over all possible nulls. And what we're going to see is, in these problems we're going to look at, surprisingly, epsilon n of p0 varies very much as a function of p0. Different nulls are much easier to test than other nulls. And of course we could ask similar questions about estimation and confidence intervals, but for now, again, we're just going to, well, for the whole talk, we'll just focus on testing. So it's this epsilon n of p0 is the quantity we're looking for. So here I'm just, this is what I just said, is that typically in a lot of minimax theory, we don't distinguish between epsilon n and epsilon n of p0. And certainly in certain sufficiently homogeneous problems, the kind that we teach in our classes and so on, it wouldn't matter if you focused on the local or global minimax rate, you would get the same rate. But in these specific problems I'm going to talk about, we're going to see that they can be very, very different. And that's what I'll be focusing on. So the local minimax rate, in other words, provides a much more refined picture of the statistical difficulty of the problem. So let's start with multinomials, which will be a review of what I learned from CS theory, some extensions that we did, Siva and I, and then, time permitting, depending on how long it takes me to talk, we'll get to the density version of this, but we'll start with the multinomial talk. By the way, so I guess I should go for, how long am I supposed to talk for, Nicole? Like 45, 50 minutes?
Yeah, something like that.
Okay. Yeah. All right. Good. So multinomials. Well, even in older, more classical work, Karl Morris, my late colleague Steve Feinberg and various others, people already, of course, were concerned even many years ago about what happens when the number of categories was large. This is certainly not a new concern, although it's a renewed concern. And there have been global minimax theory was done by Liam Paninsky. Many of you know Liam, he's at Columbia, and also a lot of work, as I say, in computer science, in the computer science literature. They call it property testing, which is just their word for hypothesis testing. So here's the notation. We have this multinomial vector, P1 to PD, without loss of generality. I'm going to assume they're ordered from largest to smallest. And now what we want to do is I want to tell you what the local and global minimax rates are without any additional assumptions. So here's where in a lot of the statistics literature, and I don't mean this critically, there's just a lot of nice papers about high-dimensional multinomial testing, but usually the first thing one does is we're going to add the following 3 assumptions, and there'll be a list of assumptions, and it's also that we can get familiar asymptotics. We're not going to allow that here. The entire simplex is now allowed. There are no additional assumptions. So we really are in this distribution-free world because it's just a multinomial without further assumptions. And we want to look at the global and local minimax rates. And again, we're going to allow D to grow at any rate. D can grow as fast as we want. Okay, all multinomials allowed. So let me tell you first of all the global rate, which I think was found by Liam Paninsky, which is already kind of a surprise. If you've never seen the minimax literature on multinomials before, I have to say this surprised me when I saw it, because this is the answer. So this is how far can I be from the null and still have power? And the answer is D to the 1/4 over root n. And if you think about that, this is kind of shocking, because this is, first of all, the estimation rate is more like square root of D over n. This is much better than that. And what it says, actually, is you only need about, for epsilon n to be small, you only need the sample size to be about the square root of D. So if you think about what that means, I've got this huge multinomial, zillions of categories. Say it's, multinomial with 1 million categories. But let me pick something I can take the square root of. 100,000 categories. And you only need about 100 observations to test this, which means most of the categories are empty. You never even see them. So it's kind of shocking that you get data. You don't have enough data to even see most of the categories, and yet you already can get a high-powered test. And this, to me, was rather surprising when I first saw this. And this is even just the global minimax rate. We haven't even got to the good stuff yet. So that global rate, I guess I should have put the year that was down, but it's not that old. I think it was a fairly recent result. And so you can have good power even when most cells are empty. But now here's where things get really interesting, which is what happens if I haven't said anything locally. I didn't say what the null was. This is a general result about all nulls. But what if I asked them about how much data do I need for a particular null distribution? And this is where the computer science literature comes in. So for those of you who don't know, let me just tell the Valiant story. Pardon me while I... Les Valiant is a very famous computer scientist who won the, I guess the Turing Award, is that whatever the sort of Nobel Prize in computer science is called? I think it's the Turing Award. And he has 2 sons, Greg Valiant and Paul Valiant, who are also theoretical computer scientists. And this is the 2 sons. So this is their paper from 2014. I'm going to describe their result, which was, this is the paper that Siva pointed me to that got me interested in this. So we're going to take this multinomial, and we're going to divide it into 2 pieces. The tail, which is just, what the formula says are just the small p's, remember I've ordered them, and the bulk, which are just the big p's. So we're just going to chop it up into the small ones and the big ones. And now we're going to do a very strange thing, which is we're going to compute the 2/3 norm of the bulk. So we take the big p's, and we compute the 2/3 norm. Just sum up the p's to the 2/3. And I have to say, I was trying to think, are there other places in our field where I've seen people use the 2/3 norm, and I honestly can't think of another one. Maybe there are other ones, but this was another surprise for me. I looked at this and said, 2/3 norm, that can't possibly be correct. I've seen the L2 norm, the L1 norm, a few other norms here and there, L-infinity norm. 2/3 norm I've never seen before, but this is what we're computing. So this V, you can even ignore the bulk and tail part if you're getting tired, it's late in the day, just think of V as the 2/3 norm of the null, whatever that is. And here's their result, which roughly says that, I should have just written more simply, that I guess I don't have a pointer, but just ignore that there's two equations, in fact. I should have just put one equation. The minimax local rate is the square root of, basically, the 2/3 norm over n. The 2/3 norm over n. So this, to me, again, was shocking, because, first of all, why the 2/3 norm? And it's also, we're going to see that the 2/3 norm, what is that? It can vary from very small to very large. So here I've just stated it more hand-wavingly, which is just that the separation rate is the 2/3 norm over n square root. How much can that 2/3 norm vary over the simplex? Well, first of all, let's also notice, by the way, that I didn't say anything about d being finite. It could even be infinite, and the 2/3 norm could be finite. But if we go back to d being large but finite, it can vary from, if you have a sparse multinomial, by which I mean most of the cells, there's a few cells with high probability, and then a lot of the cells have very low probability. Let's call that a sparse multinomial. That norm can be close to 1. That means the rate would be like square root of 1 over n, despite the fact that d might be 1,000,000. So that tells you that some nulls can be very, very easy to test, and which ones are they? The sparse nulls. On the other hand, the worst case, which gets back to Paninsky's rate, is if it was uniform, and then you get the square root of d, which if I put it in, I get d to the 1/4 over root n. So the existing rate was actually only a very crude summary, because it's the worst rate, it's the uniform, and the uniform is the hardest one to test, as it turns out. So this is showing how much the testing problem varies in difficulty. Roughly speaking, when you're near the edge of the simplex, you have an easy testing problem, and when you're near the center of the simplex, you have a hard testing problem. So there's the global rate again. Here's the, an extreme, if P0, this is just repeating what I said, is concentrated mostly on S categories, where S is small, you can see again it gets very close to a very, very fast rate of convergence. You can even do infinite multinomials here, and you can still have, and this is where the truncation comes in. Remember I talked about the bulk and the tail, that even though it's infinite, the bulk always has a finite 2/3 norm. And so what will happen is you'll get very weird rates depending on whether, for example, does it go down like a power law, does it go down like a Poisson, and I'll show you some examples of this actually in a minute. All right, so that is just theory. That just says, in theory, we can tell you how far you have to be from the null. It's this far, and then you should have lots of power. But what test do you use? What is the actual test you do to get that rate? Or in other words, how do you get an upper bound? Well, you get an upper bound by actually constructing a test. And here comes another surprise. Now, this is from the same paper, from the Valiant brothers, which is they constructed a very simple and explicit test for this. And what we learned in this is our favorites, like the likelihood ratio test, mult, and the chi-square test, really bad. All right, so here's the test. It looks just like the chi-square test, right? So xi here are the counts. Xi is the count in the ith cell. N times P0, as usual, is the expected value under the null. There's a minus xi is a centering term. That's less important. This is just centering it to mean 0 under the null. And there's that 2/3 again in the denominator. Very, so it almost looks like a chi-square test, except we're dividing by p to the 2/3 instead of p. And you think, can that really have that big an effect? And I'm going to show you in the simulations in a minute that it actually has a huge effect. And it is provably the optimal test. This is the minimax test. So, or a minimax test, I guess I should say, because there's other tests that can come close to this. There is one problem here, though, which is the way that it's stated in their paper is I have to say what distance I want to test against. Remember, I stated the alternative as if we want to test against epsilon far away, but we don't really do tests like that in statistics, right? We just say the null or not the null. Their test actually requires that you specify the distance, which is, from the computer science literature, I guess they don't worry too much about that, but no one's going to use it in statistics. So I'm going to show you a version we have that gets rid of the epsilon. But let me just show you in simulations how this actually works. You know what? I have to admit that when I saw the theory, I was a bit skeptical. And I said again to my young co-author, when we simulate this, it's not going to work. I said, trust me, the likelihood ratio test is going to win. And he said, okay, let's try it and see. And I hate to admit how many times he's been right and I've been wrong. I guess I'm getting old. But here you go. So on the left, we're going to do the uniform case. And what I'm showing you is the power curve of 3 tests as the alternative moves farther from the null. And the blue test is the chi-square test. So I was kind of right. For under a uniform null, the chi-square test does pretty good. You can see the power, it's got the highest power, and it's increasing as you get further from the null. And the orange or red, whatever that is the likelihood ratio test. So that looks pretty good. And their test actually doesn't do quite as good, which is not a contradiction, remember, because we're talking about minimax theory. Worst cases, no one's saying this is necessarily a worst case. But the test still does pretty good. You can still see that their test, the computer science test, still has respectable power, and it increases as you get further from the null. But that's the uniform case, and that's the one that's typically studied most often in our literature. Now let's take a different null. So I'm going to take a power law null, by which I just mean I'm taking a multinomial that starts off big and decays as some power law. I forget what power we chose exactly. And what I'm showing you is very typical. This was not cherry-picked, but you can see the 2 curves that have no power are the likelihood ratio test and the chi-square test. And the yellow test is their test. And you can just see it crushes everything that I've been teaching students for the last 30 years. So this is pretty convincing, actually, that this is not just interesting theory, but I would actually tell people that they should use this test instead of the chi-square test now when you're doing high-dimensional multinomials. And in our paper, by the way, in our Annals of Applied Statistics paper, we have quite extensive simulations. And this is pretty much the rule, not the exception. That this test just works very, very well. And so I actually think in routine practice we should be using this computer science test. The reason why our traditional tests fail, basically, is that when you get to low probability p-zeros, we have a p0 on the bottom instead of a p0 2/3. It turns out to matter a lot. It turns out that blows up the variance of the statistic whenever you have low probability cells. And the same thing happens to the likelihood ratio test and so on. And so our classical tests just don't work well in practice, and they're not even minimax. They're not even globally minimax, let alone locally minimax. So I'm actually, it's a bit radical, but I actually think we should give up our as much as I love the chi-square test, I think we should give up the chi-square test and the likelihood ratio test for multinomials, at least, because really this test provably and in simulations dominates our classical tests. You might wonder, though, can't we just modify the chi-square test a little bit and still get something which works well, but doesn't require me to specify a particular distance epsilon, which their test does? And this is something we did. And it turns out to be surprisingly simple to fix the chi-square test. So if you don't want to depart completely from our favorite test, all you have to do is the following trick. I've written down the chi-square test. I've gotten used to doing what the computer scientists do, which is always centering the test, which is why there's a minus x, which turns out to actually reduce the variance a bit and has mean 0 under the null. More importantly, on the bottom, instead of dividing through by what we usually divide through, which would be something like p0 or n times p0, you divide through by p0 until it gets smaller than 1 over d, and then you just truncate that. You just don't let the bottom get small. And it turns out we were able to show that this is actually globally minimax. And it's not locally minimax, but it's close to locally minimax. And this is really easy, and this doesn't require specifying the alternative in any detail. And so this works really well, which we show in our paper. One thing I should have said was that the Valiant test that I showed you, I lied a little bit. There's more to it than I put on the screen. It's actually, you have to conduct two tests, of which I only showed you one. One on the bulk and one on the tail. So it's actually a little bit fiddly, and there's some details I've omitted which makes the test a little bit difficult to do. This, you don't have to do that. So this is like, for us, the go-to test. This doesn't require a 2-stage test. You just do this trivial modification to the chi-square test, and now you have a globally minimax test. And here's just, again, some simulations. I've added in our test, which is, you can't, in the first picture, you can't even tell the difference between that and one of the other tests, I think the likelihood ratio test. And then the second one, even though it's not locally minimax, it's pretty close to locally minimax. So the purple test is the CS test, which again is a little bit more complicated than I've let on. The orange test is our modified chi-square test, which you can see is very close to being locally minimax, and crushes again the usual chi-square test. So the upshot here is it's really easy to fix the chi-square test, and it really actually in practice makes a big difference. The basic insight here is that around the uniform you can do anything you want. It turns out there isn't much distinction. But when you're away from the uniform, you do need to do some sort of modification of all the things we're familiar with. Here's another, let me just check my time. Maybe I'll skip this. We have another test which is actually within log factors of being locally minimax, and again is a bit simpler than their test. But I'm going to skip that because no, I'm wasting too much time on multinomials. So I want to get on to densities. Okay. So now we thought, well, can't we take everything we've learned and transport that to deal with density functions? The answer is yes, although this turned out to take us much longer than we thought because it was trickier than we thought. So same problem. I've just got n observations. I'm just going to restrict myself to densities again that are a kind of minimal smoothness assumption. Lipschitz smooth. Actually, there are ways to do even less smoothness than that, but today we'll just do Lipschitz. So L here controls the amount of smoothness. And everything I'm about to say we've done in d dimensions, but for now I'm just going to focus on the one-dimensional case just to keep it simple. Here I mentioned, yes, you can use something called the Wasserstein distance to handle even less smooth cases than Lipschitz, but we're focusing on Lipschitz. So first, let's go to what's known about this. So I mentioned Inkster. Inkster has many, many papers about this and related problems. And so in his papers, so I'm going to cite one of his famous results, the domain will be just 0, 1, so bounded domain. The null will be uniform, and the Lipschitz smoothness will be fixed. And then he proved that the minimax rate is 1 over n to the 2/5. So he pretty much nailed that. And let me just say also what he figured out what the optimal test is, which is to bin the data and do a chi-square test. So he pretty much settled how to do this, and admittedly a pretty simple case. I should say that, of course, a non-composite null is obviously an oversimplified case that doesn't come up very often in practice. But this is, again, just the starting point, and there's a lot of extensions to composite nulls. So this is, again, just a fixed distribution, in this case uniform. And surprisingly, it wasn't extended to d dimensions until, as far as we know, a paper by Arias Castro in 2016. There are strong assumptions here, though. L is fixed, there's a bounded domain, and it turns out that the uniform null, again, is very strong. Just as we saw, that's not surprising now, I guess, that we did the multinomial case, that the uniform null is very different from other nulls, and it's going to be the same here, too. Inkster mentions this, and he suggests something, which is the way I thought of doing this, admittedly, when I first thought about this, is, well, can't we just do like a CDF transformation for a non-uniform, make it uniform, do the test on that scale, and then transform back? That doesn't work. So that I thought that would work. And what the problem with that is you're basically not staying inside your smoothness class anymore. You've effectively, instead of a Lipschitz class, you have some sort of weird transform Lipschitz class, and it's not clear what that even means anymore. So the obvious thing, which is to do like an inverse integral transform, unfortunately doesn't work. And you'll see it's actually a little bit more complicated how we have to deal with this. So what's the answer? So we're going to have to define, remember we defined the 2/3 norm for multinomials, and we spent a long time trying to figure out there must be a corresponding functional in the density case. I thought maybe it's the 2/3 norm. It's not. It took us a while to figure out what it is. So here's what it is. Again, we need this notion of a bulk and a tail. Bulk here is a bit simpler. It's just this. It's just the set with probability, say 1 minus epsilon, which is smallest Lebesgue measure. So it's the smallest set with probability 1 minus epsilon under the null. That's the bulk. And now the critical functional turns out to be the integral of the square root of the null over the bulk. This just turns out to be, and I wish I had intuition for why this was true, the math just comes out this way, and this just turns out to be the critical functional. And this constraining it to this bulk is critical because it's not true for all densities that the integral of the square root of the density is finite even. It can be very easy to construct examples where it's infinite. But this functional, as we've defined it, is always finite. So this is somehow going to be the thing that measures the difficulty of the problem. And here's the answer. It turns out that the local minimax testing rate is the Lipschitz constant, Ln, which we're allowing to change now and then, this square root functional, t, which is somehow measuring, you should really think of it as measuring tail thickness in some sense, over n squared all to the 1/5. And this completely characterizes, this is tight up to constants, so this completely characterizes the statistical difficulty of this testing problem. And again, we don't even have to assume that the domain is bounded. And once again, we're going to see that this t of b0 can vary quite a bit. So here's some examples. If I just take uniform from, say, 0 to b, the epsilon you get is this, which looks like Ingster's, but you can see even the range of the null comes into it. For a very, very spiky null, which you might think of as, what I mean is like a triangular shaped thing, you might think of that as, shouldn't that be a hard one? Actually, so it turns out that's an easy thing to test, and that's, you get a rate of 1 over n to the 2/5, and the Lipschitz constant L even drops out, somewhat surprisingly. For Gaussians, you get the sigma squared pops into the rate, so it kind of makes sense, right? Higher sigma squared, more noise, harder to test. For Cauchys, you get this extra log factor, but so far, it's all in the constants, right? We're still getting, the sample size is still like, there's a 1 over n squared and then there's a 1/5, so it's 1 over n to the 2/5. But if you go even thicker tailed, like a Pareto distribution, it turns out that it leaks into the rate, and so if you look at what I've got there, the rate is actually slower than n to the 2/5. So the way that this functional is coming into it basically is it's telling you that thick-tailed distributions, and I guess in retrospect maybe this is not so surprising, but thick-tailed distributions are harder to test. But the interesting thing is we can make that extremely precise here. And so the high-level ideas, proof ideas here is, do I want to go through this? Yeah, this is actually, turns out to be important for actually constructing, how do you actually construct a test? So this kind of comes to us from the way you prove the bounds. A lot of the proofs, and this was true for Ingster, work by binning things. I mentioned Ingster basically cut everything into bins. And then using, multinomial goodness of fit theory. So that's kind of what we did too. You have to bin things. But here's the thing. All of Ingster's theory and most of the existing theory just use uniform bins or inverse integral bins, bins that try to make things have the same probability. In fact, most tests, right, when they talk about goodness of fit testing by binning, that's what they do. They either use, most often, equally spaced bins or bins that are larger where there's higher probability. And we tried that too, and that doesn't work either for constructing the test or for the proofs. It turns out to be the opposite. So that was the first thing we tried. I guess I'm just saying that. We tried fixed with bins. We could not prove a tight lower bound or construct an adequate test doing that. It turns out what the right answer is, and I'm just stating this on the slide, but it took us a long time to figure this out, is you need to use bins whose bin width, roughly speaking, varies like square root of p. And it's a little bit counterintuitive that in areas with higher density, I thought we should make smaller bins because you have more data there. You need to do exactly the opposite. You need to make wider bins there. And I can try to explain why later maybe, but it allows us to manipulate the density while staying with enough to create a proof while staying in the smoothness class. That's the big difference between this and the multinomial problem. So somehow we have to come up with bins so that the width of each bin is roughly speaking about the size of the square root of the density in the center of the bin. And it's in one dimension, that's easy. In higher dimensions, it's not obvious how to do this. So the way we use this in for proving the lower bounds. I'm not obviously looking at the proofs, but the typical way one proves, minimax bounds is you take your null density and you create many small perturbations, and you use these bins to create these perturbations, and then you take the average of all those perturbations and you basically use like a Neyman Pearson test between those two things. So there's a null on the left. On the right are a bunch of, I don't know how well it shows up, but a bunch of little perturbations. Hopefully you can see those. If not, there's little wiggles on there. You take all the guys on the right, you average them, and you get a new alternative, and now you basically analyze the likelihood ratio test between those, and that gives you the minimax lower bound. That's the main thing. But the technical challenge here is, again, when P0 is not uniform, these perturbations, it turns out, cannot be, as I said, equally spaced. So we have to use these adaptive bins. And the same bins, again, will be used to actually construct a real test that you're going to see actually works in practice. Before I go tell you a little bit more about these adaptive bins, because this turns out to be sort of important both for the theory and for the practice, let me just say that everything I've said so far was about one dimension, and I'm not going to go through the high dimensional stuff or the d-dimensional stuff, except to say that everywhere you saw like square root before really should be gamma, where gamma is 2 over 3 plus the dimension. And when the dimension is 1, that becomes a half. So everything I just said extends to d dimensions very easily, and it's just that the functional that we're talking about is no longer square root, it's some other thing, but it's p raised to a power. But to actually implement this test, or for that matter to do the proofs, we had to think, how do you actually construct a binning that now has the property that we have bigger bins, p to the gamma, when the density is big, and smaller when the density is small, and have a constructive way to do it? How do you know that you're going to end up with something that satisfies it at the end? And this is actually a little bit puzzling. But if you can do it, then we could say that the minimax rate in general, this is now the d-dimensional rate, is 1 over, the power is 1 over 4 plus d, and again you just have that functional t, except that instead of square root, it's got that power gamma. But this is the next holdup, is again, we need to partition it. And this is both for doing the theory and for constructing the test. We need to create a partition of the space such that each element of the partition is of size, roughly speaking, a volume p to the d gamma. So that gamma, think of it as like a half. And it's not even obvious that there exists such a partition. How do you know, given a continuous function, that there exists a finite partition such that everywhere in that partition, the volume of that particular partition element happens to agree with roughly the size of p everywhere in that region? And if you kind of stop and think about it, it's kind of not so easy to convince yourself that even exists, let alone how to construct it. So finally, we have this, and I say we, I have to give lots of credit. I forgot to do this, that my young colleague has all the good ideas here. He came in my office and said, I think I know how to do it, and he was right. Which is a constructive algorithm to create a partition which satisfies this property that the volume is proportional to square root of p and everything. And here's what it looks like. So on the left is a density, and I'll tell you what, basically in words, what the algorithm does. You basically proceed in a multi-scale way, much like, for those of you familiar with wavelets, it's a similar kind of construction. You just cut that picture on the left into 4 pieces. So you just cut it in half vertically and horizontally. Now you ask yourself the following question. Each of those 4 squares, is the maximum and the minimum of the density pretty close? So they don't vary much. And is the volume of the density proportional to p to the gamma? And if it is, you're done. If it's not, you split that cell again recursively. So it's a recursive partitioning scheme. And you keep going until you stop. And so we've done that on the right, and you can see the result of running this algorithm. And we were able to show that this is guaranteed to stop in finitely many steps, and it has exactly the properties that I just said. That when it's complete, it will have this property that the volume is proportional to p to the gamma. And this is critical both for constructing the test and the proof. And by the way, one thing we kind of learned in all this was that this part is the most important part. That you can take almost any test. I'm going to show you the mini-max test in a minute, but you can take any test you want. But if you use this binning scheme, it'll work way better. So it's this adaptive partitioning turns out in practice to be actually something that has a huge effect on the power. So here's an example. Just ignore the blue line. So just focus on the red line is the usual. In the paper we have lots of other tests we compare it to, but here I'm just showing you two, which is the red one is the usual Kolmogorov-Smirnov test. This is testing for a Gaussian null. The black one, what we've done is done that adaptive binning, then we took the cell counts, then we applied the minimax multinomial test to that binning. And you can see the dramatic increase in power. And again, I didn't cherry pick this. This is actually pretty typical. So this actually leads to a really significant improvement in the power. And again, let me just reiterate before I conclude, it's going a bit longer, that it really seems to be the binning, in some sense, that's more important than the test. So now, I'll summarize. So for testing Lifshitz densities, we do see the same phenomena that we saw for multinomials, that there's interesting local minimax phenomena. Different densities are harder or easier to test than others. The typical assumptions like bounded domain, uniform null, fixed amount of smoothness, you miss all of that information about how much the difficulty of the problem varies over the parameter space. And we've given you local, tight local bounds. There's other extensions I'm not going to talk about. This adaptive binning procedure, I think, is just kind of interesting in its own right, and I don't fully understand it myself yet. It sort of works. It sort of was forced upon us by the math, but I feel like there's something else going on that we don't understand. Eventually, though, I actually don't think binning is the right way to do it. I think for low smoothness things, binning is right. If you actually did want to use more smoothness, so you say you like Sobolev spaces, I don't think binning is the right way to go. We don't actually know how to get the local minimax rates and tests in the smoother case yet. That's still an open question. In fact, let me conclude by telling you what our current work is and what I think are some open questions. Two sample testing. So again, I have to give credit to the CS theory, where they have worked out very carefully what the, say, comparing two multinomials, the rates, I'm not going to put them down here, they're very surprising. They're not at all intuitive. But oddly enough, in this case, the chi-squared test is minimax. So there's something weird going on that in some cases our familiar tests turn out to be the right thing to do, but in some cases not. And I must say, I don't have time to go into it, but the notion of local minimaxity is much more subtle here. In fact, we don't even know how to clearly define what we mean by local minimaxity in two-sample testing. So already in two-sample testing, there's some weird stuff happening. We don't know how to do more smoothness. An interesting case I mentioned at the beginning is to deal with less smoothness, and there's actually quite a bit known about that for testing, but very little known about that in terms of confidence intervals. Another interesting case is conditional independence. Say you want to construct a graphical model or a log linear model. Once again, our standard tests in the high-dimensional case are not minimax, and very little is known about this case. In fact, we know of one paper on it, and even there, it's not completely worked out. So it's surprisingly something we've been dealing with for so many years, log linear models and graphical models. When you have a lot of cells in the table, the minimax theory is not even completely known at this point. And testing for clusters is another problem that we're thinking about, where again, there's a lot of non-standard things going on. Lastly, this is all about testing. I really want to get away from testing. I mean, this just took a lot longer and was a lot harder than we thought. We really want to start talking about what does it mean to talk about locally optimal confidence sets and things like that. So hopefully in the future, I'll be able to, if you're interested, send you a paper on optimal confidence sets, but that's future work. And that's it. Thanks very much for your attention.
Questions for our speaker?
Okay. One thing you said earlier sounds too good to be true. Like suppose you have, 1 million cells. You're saying, well, with 1,000, do this kind of test. People say, how could it possibly be? Now, of course, you have some restriction, but this comes up all the time in testing where you have a rare event, you don't get much. I mean, that's why, in classical things, you want n times greater than 5, or what's some number like that, you can get smaller. But if you really haven't observed, it's something out in the tail is rare, but you don't know how rare, and you're trying to test an alternative, of something of that kind of order, it seems almost impossible. I mean, I think there's something a little hidden. I believe when you showed that first graph of how, your new test shoots up there, from those really small epsilons, which might be what you're really concerned with. I think it's impossible. There's no way you could be able to tell whether something is a 1 in a million or 1 in 1,000 if you only have 100 observations. I just don't think there's any way around it. So there's something else that's a little hidden there, I think.
Yeah, so, okay, I'll go back to this one. Yes, it does seem that the minimax rate seems too good to be true. I felt that way too. So one thing is that this brings home a really important point, which is that testing turns out to be way easier than estimation, because if you were trying to estimate it, you could not. But testing is just easier, and what happens, so the minimax test, the global minimax test, is something like, you just count the things like the number of collisions, like how often you get 2 in a bin. And it turns out that when you're d to the 1/4 over root n away, which is not 0, so it's small, but it's not, super close to 0 either. There's still enough information in things like collisions that you actually can test it. I agree with you, it's surprising. And now there are constants. That's the rate. So, if we were to do a much more careful simulation and that was to blow up the lower end of the scale, we would see what you're talking about, which is you're going to get to a point where you're just not going to be able to test them. But I think what's surprising is that how far you have to go down is further down than you probably think intuitively. I think it really is surprising, but it is true. But the best thing I can suggest is, to simulate it, and I really had to simulate it and see for myself that whether I would believe it or not. But it is much easier to test those things than you think it is. It's just surprising, but there's enough things like coincidences, or how many empty cells there are, things like that, that have a little bit of information in them that will help you actually have non-trivial power.
If you were to consider a sort of a gamma norm that you wrote in the end, is there a way to sort of look at it as a continuum from 0 to 1 and show that the 2/3 is the optimal one?
So I think what you're really asking me is, where does that 2/3 norm come from?
Yes.
So I have to admit, it's one of those things, when you work through the proofs, it pops out. And I've tried to develop intuition for it, and I honestly don't have any. And this is very frustrating. And in fact, I mentioned the Valiant brothers. I spoke to Greg Valiant, and I asked him, how did you guys know it was the 2/3 norm? And he said, listen, he goes, what happened was, I was working on the upper bound, my brother was working on the lower bound, and we kept saying, I've got the answer, and we were disagreeing, and we just kept working at it, and we eventually got the same answer. It was the 2/3 norm. And, but they don't have the intuition about it either. I'll tell you where it comes up in the proofs is that you approximate all these multinomials first of all with Poissons. You do a Poisson kind of coupling thing. And then if you look at how Hellmann's distance behaves with Poissons, 2/3 start to pop out just because of the nature of a Poisson. That's where the 2/3 comes from. But I don't really honestly have any sort of statistical intuition for why it's the 2/3 norm. I've been wanting to come up with some notion of intuition, but I don't have one.
I was wondering that for the density case, do you have a binning idea that you have yourself skeptical about? I was wondering how it behaves about when there's a curse of dimensionality happening when the densities are concentrated around the edges.
Oh, yes, that's a good point. So the D meant something different, right? And so in the multinomial, the D was the number of cells, and that we were allowing that to be large. In the density stuff, D was fixed. I should have said that. So yes, there is a curse of dimensionality in the density case. And everything I said, we have the explicit dependence on D, but D has to be fixed to have any power without extra assumptions. In fact, the Arias Castro paper that I referred to, the name of that paper is Don't Forget the Curse of Dimensionality, because he was responding to the fact that there's this whole world, especially in machine learning, where they're kind of in love with reproducing kernel Hilbert spaces, which is great. I like them too. But in testing, there's these results that claim that there's no curse of dimensionality in hypothesis testing if you work in reproducing kernel Hilbert spaces. And they wrote their paper to say that's not true because you're constraining the size of the ball, the reproducing kernel Hilbert space ball, so much that it's almost a parametric problem. So when you express a property like in terms of Sobolev spaces and things like that, there is a D, and yes, there is a curse of dimensionality there. And we don't have any solution to that except to add extra assumptions.
Any other questions? Yeah.
I think for the one-dimensional case, the minimax rate is derived by the Eggers term. You have derived the minimax rate, but if you consider the multiple dimension density function, do you think the rate will be the same?
Oh no, that's what the gamma was. So the rate in d dimensions is 2 over 4 plus d. That's the exponent. So there is explicitly dimension dependence.
Okay, well, if no further questions, let's thank Larry again, and of course we have time to socialize over snacks.
Scenario is that when a cell phone increases size from 3.5 to 4.5 at our lowest end of our confidence interval, we go from 329 minutes we'd expect someone to be talking to 372. Well, and so at b equals 43.8, 1 unit increase, just like this, gets us exactly the same increase as the value of the slope. And then we go to the most, the best. Same thing. So this minus this equals that. That is remarkable. So now, so I'm a big fat cat with a top hat, and I want to make money. I want to build a bigger cell phone. I've got this data. So now, what I know, and this is actually, I mean, it's not really that great, but what I know is that if I make a cell phone that's, say, 1 inch larger, people will talk 43 minutes more because I also own a cell phone service company, and I just put up more towers. And so I calculated that, I did this, and I calculated that I'll make 43 more minutes per customer if I increase cell phone by 1 inch. And if this happens, I'm retiring because 150 minutes. But either way, the point is that 95% of the time, 19 out of 20 times, this, well, let me backtrack. Now I have a 95% confidence